Ever wonder why your phone wakes up the instant your finger lands on the screen? But when you tap it with a pencil, nothing happens. And in winter, your favorite gloves make the screen completely dead. It feels like a button, but the screen is not really reacting to pressure. It is reacting to something living inside you. Stickman is cold. He is wearing thick winter gloves. He tries to press play on his music app. The screen does nothing. The song does not start. He takes off one glove and tries again with his bare finger. The song starts immediately. Same screen, same amount of pressure, very different result. So what is the screen actually listening for? Your brain tells you the screen is a button. Press harder, get a result. That is how piano keys work. That is how a light switch works. That is how a doorbell works. So it is normal to assume the screen is the same. But a touch screen is not a button at all. It is a sheet of glass that can feel electricity. It cannot feel force, but it can feel charge. And charge is a word we need to understand properly. Stickman presses a wall light switch with his finger. The light turns on. He nods, satisfied with the physics. He then walks to his phone and presses it with the same force. The phone does not care how hard he pressed. It only cares what touched it. Let us talk about what is inside your finger. Your body is mostly water. Salt water, to be exact. That salt water is full of tiny charged particles. These particles are called ions. Ions are atoms with a missing or extra electron. Because ions can move, salt water can carry electricity. In science, we call a material that carries electricity a conductor. Copper is a conductor. Salt water is a conductor. You are a conductor. A wooden pencil is not a conductor. It is an insulator. Plastic is an insulator. Rubber is an insulator. Thick fabric is an insulator. This is why your glove blocks the screen. The rubber and fabric are insulators. Now we need a second idea. We need to talk about charge. All matter is made of atoms. Atoms have a center called a nucleus. Around the nucleus, tiny particles called electrons orbit. Electrons have a negative charge. The nucleus has a positive charge. Normally, an atom has the same number of electrons and protons, so it is neutral. If an atom gains an extra electron, it becomes negatively charged. If it loses an electron, it becomes positively charged. Opposite charges attract, like charges repel. This is a universal rule. Picture two magnets. The same poles push apart. The opposite poles snap together. Charge behaves the same way, even though it is not a magnet. When electrons gather in one spot, they push each other away. When you scuff your socks on a carpet, electrons jump onto you. Now you have extra electrons. You are negatively charged. When you touch a doorknob, those extra electrons jump off. That is a static shock. Static electricity is just a buildup of extra charge on a surface. Your body can hold charge. Your finger can hold charge. And this is exactly what a touchscreen is designed to detect. Now we get to the big word, capacitance. Capacitance is the ability of a system to store electrical charge. Think of it like a tiny bucket that can hold electrons. A bigger bucket can hold more water. A bigger capacitor can hold more charge. Inside the phone screen, there is a grid of these tiny buckets. Each bucket is called a capacitor. Capacitors are everywhere in electronics. A capacitor is just two conductive plates separated by an insulator. One plate collects positive charge. The other plate collects negative charge. The insulator in the middle stops the charge from jumping across. When you connect a battery, charge builds up on both plates. Energy is stored. In your phone, the top plate is a clear conductive layer on the glass. The bottom plate is another conductive layer underneath. Between them is a thin layer of glass or plastic, which is an insulator. Every tiny square of this sandwich is a capacitor, and every one of them is holding a small, steady amount of charge. Now here's the clever part. These capacitors can sense nearby objects. Each capacitor projects a tiny electric field outward through the glass. An electric field is an invisible region where charge can feel a push or pull. You cannot see it, but you can draw it with arrows showing the force. Every charged object is surrounded by an electric field. So is every capacitor. When a conductor enters this field, it changes the field shape. Concentrated charge on the top plate creates a field reaching outward. A nearby conductor, like your finger, distorts that field. Your finger does not even need to touch the glass. It just needs to be close enough to change the field. When your finger is close, the field latches onto the salt water inside you. The salt water in your body provides a path for the charge to drain into you. A small amount of charge flows from the capacitor into your finger. The capacitor loses a tiny bit of its stored charge. Its voltage drops slightly. Voltage is a measure of electrical push between 2 points. Think of voltage like water pressure in a pipe. Higher pressure means more push. Lower pressure means less push. When charge drains into your finger, the pressure inside the capacitor drops. A sensor chip underneath the glass measures every single capacitor all the time. It checks thousands of them in a fraction of a second. It notices the one capacitor that just lost a little bit of charge. That tells the phone the exact location of the touch. Your glove cannot do this. The rubber and fabric are insulators. The field cannot latch onto the fabric, so no charge drains. The capacitor stays full. The sensor sees no change. Nothing happens. A wooden pencil cannot do this either. Wood is an insulator. Only a conductor can pull charge out of the capacitor's field. Some special styluses have a conductive rubber tip. They work on touch screens. That tip is a small conductor designed to fake a finger. Capacitance is not a one-time thing. It happens as long as the field is disturbed. When you slide your finger, new capacitors keep losing charge as the field follows. The chip reports a stream of positions. The screen sees a smooth swipe. When you lift your finger, the field returns to normal. The capacitors refill their charge from the battery. The screen is ready again. This whole process happens hundreds of times per second. It feels instant. Now let us put it all together and see the engineering. Under the glass, there is a thin pattern called an indium tin oxide grid. It is a transparent metal. You can see through it, but it carries charge. The grid is laid out in rows going one way and columns going the other way. Wherever a row crosses a column, there is a small capacitor. Each crossing point is one touch sensor. A modern phone has thousands of them. The grid is connected to a controller chip at the edge of the screen. The chip takes turns sending a tiny electrical pulse to each row. Then it listens on every column for any drop in charge. This is called mutual capacitance. Two plates talk to each other. When your finger lands, it changes the coupling between one row and one column. The chip spots the exact row and column. It does a quick math problem. It calculates the center of the touch to within a fraction of a millimeter. This is why your phone can tell a tap from a long press. It is also why the phone can track multiple fingers at once. Each finger disturbs a different crossing point on the grid. The chip sees several drops at once. It labels them as separate touches. When you pinch to zoom, the chip measures the distance between two fingers. It then tells the software to make the image bigger or smaller. All of this happens without a single moving part. There is nothing to wear out. The glass itself is not doing the work. The grid under the glass is doing it. A scratch on the surface does not break the grid. It still senses your finger. A cracked screen can still work, as long as the grid underneath is intact. This is also why water on the screen can confuse the phone. Water is a conductor. A drop of water disturbs the field, just like a finger. The chip sees many false touches and gives up. That is a wet screen ghost touch. Engineers fix this with software tricks, comparing the shape of the disturbance. The touch screen has been around for decades, but the basic physics has not changed. Charge, fields, conductors, and capacitors. Those four ideas run the whole thing. Every tap, swipe, and pinch is a tiny electrical conversation with your skin. So let us recap the whole story. Your phone screen is not a button. It is a grid of tiny capacitors. Each capacitor holds a small, steady amount of electrical charge. That charge creates a small electric field reaching out through the glass. Your finger is full of salt water. Salt water is a conductor. When your finger comes close, the field latches onto it. A small amount of charge drains from the capacitor into your finger. The voltage on that capacitor drops. The chip notices the drop and reports the exact location to the software. A pencil is wood. Wood is an insulator. No charge can drain. A glove is rubber and fabric. Both are insulators. No charge can drain. Only a conductor can disturb the field. Only a conductor gets a response. This is the whole secret behind the magic glass on your phone. It is not pressure. It is not heat. It is electricity. Thank you for watching this video. Let me know in the comments if you liked it. Don't forget to like and subscribe for more.